In this video, we're going to continue talking about chemical reactions, and we're going to focus now on oxidation reduction reactions. Oxidation reduction reactions is not a new classification of reactions. Oxidation reduction reactions are going to describe some of the reactions that we learned in the previous videos. It's just that specifically, oxidation reduction reactions involve the exchange of electrons. Combination reactions, decomposition reactions, single replacement reactions, and combustion reactions can undergo oxidation and reduction. The reason why we talk about oxidation and reduction is because as we progress in the semester, we are going to see how oxidation reduction reactions is what provides the energy that we derive from food. And biochemically, we're going to observe that later in the semester. Oxidation reduction reactions also provide the electrical energy that is stored in batteries. Let me give you an example of an oxidation reduction reaction. In the bottom right corner, we have the following reaction. Copper reacts with O2 gas to produce copper 2 oxide. What type of reaction is this? Based on the classification that we studied in the previous video. As we look at what happens in this reaction, we see that the reactants undergo a change in oxidation number, which in a few moments we're going to learn how we assign those. Elemental forms of copper and oxygen made the ionic compound copper 2 oxide. So what happens overall is that we see that elemental copper had an oxidation number of 0 because it's found in elemental form. And in the product, we observe that all of a sudden it became a cation. So because of that, we know that when cations form, there's a loss of electrons. And that process is called oxidation. Oxygen gas, on the other hand, because it's found in elemental form in the reactants, it has an oxidation number of 0. We can observe that in the product of the reaction, when that ionic compound of copper 2 oxide formed, oxygen became -2, meaning that it formed an anion. In order for an anion to form, electrons have to be accepted. So when we have a molecule or an atom, I should say, that accepts electrons, that process is called reduction. This reaction of copper and oxygen combining to make copper 2 oxide is specifically what happened to a national symbol in this country that is known as the Statue of Liberty. The Statue of Liberty is actually made out of copper. And due to the oxidation that has occurred of the copper metal, that is the main substance that the Statue of Liberty is formed, it has actually over the years developed this green solid that is copper 2 oxide. We know that as green patina. So that's why, as the picture that you can observe on the right side, the tint that the Statue of Liberty has is due to an oxidation reduction reaction that has occurred to the copper that is made out of. As I mentioned a few moments ago, when it comes to what is oxidation versus what is reduction, oxidation is going to illustrate when electrons are lost in an atom. So that means that a particular atom is oxidized. When an atom is reduced, it has gained electrons. There are different ways to remember this. You can remember it by the definition, but there are two acronyms that are typically utilized in order for students to easily remember this. We have oil rig or Leo Ger. They are showing the same thing. In oil rig, it means oxidation is losing electrons. Rig, reduction is gaining electrons. In Leoger, it says losing electrons oxidation, gaining electrons reduction. So this is just a way in which you can remember what is oxidation and what is reduction. But as I mentioned, when it comes to oxidation reduction, we have first to learn how to assign oxidation numbers for the atoms involved in our reaction. There are some general rules for calculation of oxidation number, and they are summarized in the following notes. As we observed in the previous example, any element like copper in solid form or diatomic molecules like O2 is considered that an element is by itself, so its oxidation number is 0. Next, when it comes to elements that live in group 1A, group 2A, and as a matter of fact, for group 3A, they are known to have oxidation numbers of +1, +2, and +3, as long as they are found in ionic compounds. Halogens, which live in group 7A, are usually -1 because that is their charge based on their group number. And they tend to have a positive value for their oxidation number if they're paired with oxygen. But that comes from the idea that oxygen is usually -2. Oxygen is always -1 when we find it in peroxide. But when it comes to this, I'm just going to eliminate this note of the findings in peroxide because, to be honest with you, in this class, we don't explore the oxidation number of oxygen specifically in peroxide. So let's just assume that for the purposes of this class, oxygen is always going to have an oxidation number of -2. Fluorine is a halogen, and as you can see, it's always -1. But that goes along with the idea that halogens are going to be -1. Monoatomic ions, like they live in 1A, 2A, 3A, five A, 6A, 7A, as long as they are in ionic compounds, their ionic number or oxidation number, sorry, is their ion charge. Hydrogen, it lives in 1A, but it is important to note that when we find it with nonmetals, it's going to have an oxidation number of +1, but when we find it with metals, it's going to have an oxidation number of -1. Lastly, the sum of oxidation numbers for a neutral compound is always 0, while the sum of oxidation numbers for a polyatomic ion is going to be the ion charge. After the discussion of all these rules, let's actually put them into practice. We have the following reaction. Iron 3 oxide combines with carbon to make iron and carbon monoxide. Based on the rules, there are at least one component in the reactant and one component in the product that will have an oxidation number of 0 simply because they are found in elemental form. That component is going to be in the reactant, carbon, going to have an oxidation number of 0. And in the product is going to be iron. Next, we can observe that in the reactant, we have an ionic compound, iron 3 oxide. If we break this molecule into ions, the ion charge will be their oxidation number. Our iron is +3, our oxygen is -2. And all I did was reverse the crisscrossing to find these ion charges. So what this shows me is that iron oxidation number is +3. Oxygen oxidation number is -2 in the reactant. Let's now move on to the product where we have a covalent compound, carbon monoxide. According to the rules that we just discussed, oxygen is going to be always -2. This is a neutral compound. And the reason why I know it's a neutral compound is because I don't have an overall charge here in the corner illustrated. So what this suggests is that if I add the oxidation numbers of oxygen and carbon, it must equal 0. In this molecule, because each component has a subscript of 1 that I just wrote, but it is implied, when we're trying to discover what is the oxidation number of carbon in carbon monoxide, taking into account that oxygen has an oxidation number of -2, and then we multiply by the subscript, which is 1. So overall, this is -2. We can define that if we're trying to find out this value, it has to be a digit that when we multiply it times 1, and add it to -2 is going to equal 0. So taking that into consideration, we know that via math, we can define that the oxidation number of carbon is +2. Then I organize a table in order for me to know what happened to oxidation numbers as we progress in this reaction. So in this reaction, I have iron, oxygen, and carbon. Then I have the values in the reactant. That's what R is going to represent. P is going to represent product. Then I organize what is the change in oxidation number. So first I can say iron was +3, oxygen was -2, carbon was 0. And I write down those values. +3, -2, and 0. Next, I write down what I see in the product. Iron has an oxidation number of 0 in the product. Carbon has an oxidation number of +2. Oxygen has an oxidation number of -2. Next, in order for me not to get confused of who gained electrons, who lost electrons, I like to write a number line in which if this is 0, all the values that are positive are to the right of the 0. All the negative values are to the left of the 0. Then, when I'm trying to determine what gets oxidized, it's going to be any value that has a movement from left to right. And any value that has a movement from right to left means that that atom, in terms of its oxidation number, undergoes reduction. Let me illustrate how to use this number line. So we can observe here how iron went from +3 to 0. So if I try to illustrate this, it means that my iron was here and it moved in this direction. So taking that into account, this means that this matches the directionality of reduction. So in this reaction, iron undergoes reduction. Then I see that oxygen has no change in oxidation number. That means that this atom is known as the spectator atom because there's no change of oxidation number, since in the reactant it was -2 and in the product was -2. Then it is just literally an spectator. It's just looking at the reaction and the exchange happening, but it's not involved in the exchange of electrons. Next, we can observe that overall we have the carbon atom going from 0 to +2. So if I illustrate that arrow, carbon starts at 0 and it goes towards positive side. That arrow matches oxidation. So we say that carbon undergoes oxidation. Let's continue practice with some book problems. I'm going to do with you guys letter B. First, I'm going to define what is the oxidation number of all the components in my chemical reaction. My shorthand for oxidation number is O/N. First, I'm going to try to identify if in my chemical reaction I have any elements by themselves. And I can observe that in the reactant, I have an element by itself, and in the product, I have an element by itself. So they get assigned an oxidation number of 0. Next, here in this reaction specifically, I have 2 ionic compounds, Ki and KCl. So in ionic compounds, the charge of the ions is also their oxidation number. So if I take this compound and break it into ions, and this compound and I change it into ions, I notice that potassium oxidation number is going to be +1. Iodine oxidation number is going to be -1. Potassium is going to be +1. Chlorine, it is -1. Remember that in this case, I am taking these values from the group number that each of these atoms have, because that is in essence where we get these values when we have ionic compounds. Then I make my table. I write Cl, K, and I, and I'm trying to define what is the oxidation numbers in the reactants by giving the capital R and in the product. In chlorine, it has an oxidation number of 0 in the reactant. Potassium has a +1. Iodine has a -1. In the product, iodine has a 0. Potassium has a +1. And chlorine has a -1. I redraw my number line where this is 0, this is positive, this is negative. Anything going in this direction is considered to undergo oxidation. Anything in this direction is considered going reduction. So as I explore and I observe what happens in terms of the oxidation number, I can notice that potassium remained with the same oxidation number in the reactants and in the products. What is the name for atoms that do not have a change of oxidation number in a reaction? Let's next consider what happened to chlorine and what happened to iodine. In the case of chlorine, we can observe that it went from 0 to a negative number. So that means that chlorine is undergoing reduction. In the case for iodine, we can observe that it goes from a negative number towards 0. So that means that it's undergoing oxidation. One last thing that I want to mention when it comes to this is that when we try to verbalize what is oxidation and what is reduction, we always do it in terms of the reactants. So if I'm trying to verbalize oxidation and reduction, this is the way that I word it. Cl in Cl2 is reducing. And I in Ki is oxidizing. The reason why we do this is because the elements that are undergoing oxidation and reduction, we always talk about them undergoing these processes via occurring from the point of view of the reactant, not the product.